This is the 40th lecture in a course on single agent search. And in this lecture, we're going to continue where we left off in the previous one. In the previous lecture, we looked at canonical orderings and saw how we could build those and how we could use jump points to ensure that we went around the corners of obstacles and therefore we're able to reach every state in the state space. And what we're going to do here is we're going to build a number of algorithms that then build on top of canonical orderings to be able to search more efficiently. And we're going to start from the easiest algorithm and we're going to work our way up to more complex algorithms. So I'm going to start just A star. We'll think about A star for a second here, and or I'm going to show a video actually. And then we're going to get to canonical A star. From there, we're going to go up to jump point search. And then we're going to get to bounded jump point search. And once we've gotten to bounded jump point search, then we're going to get to Canonical Dijkstra's algorithm. Sorry, and I missed one in there. We're going to get to weighted JPS as well. We'll do those in the other order, so I'll get these ordered properly here. Okay, so those are the algorithms we're going to go through in this video. And at the core, what we're thinking about is we're thinking about a best first search. Okay, so we're going to do a best first search. And in fact, we're going to do a best first search. And for most of these algorithms, we're going to be guided by F is equal to G plus H. Okay. And the only question really that's going to go on is that normally we would have a grid map. So this is our search algorithm. There'll be some exceptions, particularly the weighted jump point search in Canonical Dijkstra, but this is our search algorithm. And what we're thinking about here in this space is we're really thinking about transformations of the state space. So we want to go from a grid map to a canonical grid map. And the idea behind this is we've got our original state space, which is a grid map, and then we apply the canonical ordering on that, and that's going to give us, and we're going to get to different levels of it, but it's going to give us basically different state spaces that we can search through, and we can search through these more efficiently than we can our original state space. So it's a form of abstraction. So to demonstrate this, I'm going to start out by, I'll show a video here, and then I'll explain some of the details of what's going on. But let's go ahead and take a look at what goes on with A star when solving a particular problem. So this is a picture of A star. There's going to be a picture of A star, and the yellow state is the start state. The gray lines that are drawn are the canonical ordering, but we're not using that at all in this particular search. And the goal state is diagonally up to the right from the start state. And you'll be able to see that in a second. So if we watch A star running on this particular problem, what do we see? Well, we see it run just as we normally would expect it to run. And, in this problem, the goal is up at the top. You can see it up there. So we're just solving a normal problem here. We're searching out our space. And one thing that you can notice here is we have the red region. I apologize, red and green. I've been meaning to adjust these colors. If you're colorblind, you may have a little bit of trouble distinguishing the border, but there is a difference in color between the border states, which are green, the red states in the middle, which are the closed list. And what we see is that the closed list is entirely surrounded on all sides by the open list. So just play this again. And as we generate states, as we search here, we see this border of open states very heavily surrounds every state that is on the closed list. So there's a very strong and well-defined boundary around the states on the closed list with states that are on the open list. Okay, and now what we're going to do is we're going to solve the same or a similar problem using canonical A star. And what canonical A star is doing here is it's solving the exact same problem, except that when we run canonical A star, what we're doing is we are using the canonical ordering and we are not generating successors that would be normally generated using using our non-canonical environment. Okay, so we've really taken our state space and we've replaced it with a state space that has a different rule for successors. And so in many ways, we're using constraints to prune that. But what we notice here is around the expansions that we no longer have this border of states anymore like we had in the previous search. So I'm going to show this again twice. Let's go back to A star. So here's A star. There's a border around all of these states. And so we can see that border clearly there. And then when we use the canonical ordering, we're not going to have that border anymore. In fact, it's quite sparse. So let's take a look. I'll draw it out now in the iPad that I'm using here to explain what's going on. So what canonical A star is just A star using the canonical ordering. And what we see here for any particular problem that we might be looking at, if I think about my start state, and what I'm going to do is let's just do something really simple. Let's put a simple obstacle right here, and then we'll put the goal on the other side of that. Okay, and if we look at this problem, what we would typically see is, and I'll draw this here a little bit larger. Typically what will happen is the search is going to go straight from the start towards the goal. So we generate our search down here. And when we do this search, when I'm using a normal search, what I would expect to see is I would expect to see that around this, I'm going to generate a set of neighbors. Okay, make this a little bit neater. Okay, there's a set of neighbors around here. They're all going to be generated. And all of those states are giving us the neighbors of the states on the red line. But when I use canonical A star, so getting rid of that, when I use canonical A star, what's happening is that I know that I can reach those states by another path. In particular, the other path I could reach them by would be a path like this one, where I go diagonally and then go this way, or go diagonally and then go this way. And since I know that all the states on these purple lines, or the pink lines here, don't need to be reached by coming here and then going here, because that would not be a canonical path, then we don't even generate these states. So as I search down here, I don't generate any of these states on the open list. What's sitting on the open list are the states here, which would be from the start state moving off in that direction. And then when I search in this direction, I won't even, I do some scanning to see if there's obstacles here, but I don't have to generate into the open list any of the states here, and I don't generate into the open list any of the states here. The only thing I would possibly generate, again, just changing my color again, would be states out here. If I'm not generating all the way down, generally what would happen is I would generate the state here, I would generate a state here, and in this case, I might not even expand them because I would come down here and find the goal. But the point is that as I go along this line right here, I don't have to generate the states above it or the states below it. So as we go down the red line, we don't generate the states here. When we do decide we're going to generate them, or we're going to all from the top of this tree, we'll generate them across here. We'll get the ones across in this direction, and we'll continue that out. And then at the very end, we would come and be able to go around this obstacle to get to the goal. Whether we have to do the next layer depends on whether I have to go around the goal this way, or whether the goal is one step out from the obstacle that allows us to take a diagonal step to get there. But the idea is what's going on and why we might want to use this. So just going back to the video here, is that when I use a regular A star search, what's happening is that, this is the regular A star search. When I use this regular A star search, what happens is that we do a lot of states are put into the open list, and they're looked up in the open list to see if they're duplicates. And just by using the canonical ordering, instead of having to look them up in the open list, I do still need to look at the states and say, is there an obstacle or not, in order to find jump points that go around obstacles. But when I do that check, which is a simple access the map or can be pre-computed, that's much cheaper than going into the open list and saying, look into the open list and say, in a hash table or some other table, is this state already in here? If it isn't, what's the cost? Do I have a shorter cost to it? So that's that's a more expensive process. So by using the canonical ordering in A star, I avoid generating the states that are out around the boundary that I would normally generate. And that means that the whole search overall is going to be faster, less overhead in my data structures. The necessary node expansions are going to be still the same set of necessary node expansions, so we're not going to save node expansions. And due to tie breaking, we might actually do slightly fewer. Like on average, over a large set of problems, we might on average do 1 or 2 extra node expansions. But it's just going to be a result of tie breaking and is very, very minimal cost. But in a problem like this is going to allow us to have our data structures be more efficient. And so that's going to be an advantage for having a faster search, which is something we'd always like to have. Okay, so that's our first algorithm. And if we look at that, this is canonical A star. It is simply a best first search using f equals g plus h. We simply have a different rule that tells us how to generate our successors. And what we're going to look at then is that we can now take this idea, and what we notice here is that we can, as we generate this canonical ordering, there's not many states in here that are very interesting. In fact, inside, so this is going to get us to jump point search. When I'm doing the search or thinking about the state space in general, there's actually only 3 types of states that are interesting. The start state, the goal state. I have to make sure I have those, right? And the only other thing that's interesting are jump points. So jump point search is based on the observation that if I keep the start state, I keep the goal state, and I keep jump points, that I don't even actually have to put any other state into my search. I can just drop them out of the search and I'll be fine. So the idea would be that all these states that are going around here, if you think about these states, when I'm going down here, I have one parent and then I only have one child, and one parent and one child. And you can think about, in general, if I have a state that only has one child, instead of putting it in the open list, I can actually just immediately expand that child, and I can continue to do that as long as there's only one successor. And so something like going down here, I can just say, look, one successor, one successor, one successor, one successor, and I get to the end here and I didn't reach the goal. I reached an obstacle and there were no neighbors in the canonical ordering. So there's no reason not to actually sort of think about just scanning entirely down this portion of the path, and in skipping over this portion of the path down to this obstacle, I can immediately know that there are no states that are interesting to generate there, and I never have to put any of them in the open list or even look them up in the open list. And as I go down this path, so again, I'm following the canonical ordering, I can come down this path right here. And what I notice is that there's sort of nothing interesting. I could continue actually all the way to the end of the map. There's nothing interesting. If I wanted to, I could also stop. There's sort of nothing interesting until I hit the obstacle and then think about going around that obstacle. Now I can continue to scan my canonical ordering, but in this case, it would go around this obstacle again and again and again. And that would be problematic. And so we really need to stop the search. We don't want it to run with unbounded cost. And so proposal to stop the search is when I come to a jump point, let's stop, put that in the open list, because the cost might have actually gone up a lot. It just depends on which direction I'm jumping. If I'm going in the backwards direction, my F cost could go up quite a lot. And therefore, maybe I want to go in this backwards direction, or I don't want to go quite as far in the backwards direction, or I don't want to keep jumping around in circles so that I put in states with much higher F cost than the current best F cost. Okay, so jump point search, the idea is that when I get to these states, particularly think about this with a limited branching factor, it's only got one successor, we're just going to continue to jump. So this is the jumping policy. I'm going to jump over states until I get to something that's interesting. Now, when I'm going diagonally here, these states actually have 3 successors. And so what we're going to do is we're going to go diagonally, and then we'll jump in each of the cardinal directions, jump in the cardinal directions, jump in the cardinal directions. And I'm going to come back to that in just a second, but let's go ahead and see what's going on in jump point search when we run the algorithm. Okay, so actually I'm going to show this. We'll look at it one step at a time, and then we'll watch it running on a different problem. So let's go back to here. This is the problem we were looking at as the exercise in the previous problem. So we have the yellow state here, which is the start state. So what jump point search does is it generates the canonical ordering. until it hits the jump points. Now I've drawn these as straight lines here so that the lines are a little bit easier to distinguish from the underlying canonical ordering. But these dark lines would actually, the actual path is the canonical ordering underlying the dark path. And so on this particular, I don't remember where the goal is on this example, but the yellow state is the one we're going to expand next. But we've taken the start state, we've generated all the states we can reach according to the canonical ordering. We put them in the open list according to fcost. And at this point, we're just running a best first search. Like any other best first search, I'm basically running A star with f equals g plus h according to the fcost of my jump points. And so I'm going to take this yellow state and I'll generate its successor. I'll take this other yellow state, generate its next successor. So there's only one jump point that can be generated from that. And I'm going to continue this process until I find the goal, which is around the backside of this obstacle. Okay, so we found the goal there. And that gives us our worst, or it gives us our, how we're actually going to run our algorithm in terms of jumping. And so one of the things we'll notice here immediately is that there are very few states in the open list. But the other thing we notice is that our branching factor, where we might have had a branching factor of 8, we could have a much higher or much lower branching factor, and that depends on the state space itself. And so let's go back though and take a look at what can happen here. Okay, so we'll look at an example of this running one more time. Actually, yeah, let's just go to this other example of this running, sorry, and then we'll look at the worst case behavior and what we can do to fix it. So this is just going back to the previous example that we had. We can watch jump point search running on here. This runs slowly, so we can sort of see one step at a time. So it's stepping, and we are just really running A star, but we're running A star on top of the jump points instead of running A star on top of in the underlying grid. But there's something really important that's going on. And so let me explain what's going on here that may be a little bit hidden. And again, there's this, whether there's cost here depends on whether the amount of pre-processing that we're doing. If we don't want to do any pre-processing, then what I'm going to describe here is valid. If you do want to do a lot of pre-processing using jump point search plus, then we can reduce some of this overhead. Okay, so what's going on here? Although we're drawing the search when we put these obstacles in the state space, so I'm going to put some obstacles here, and I think about my start state, we're drawing the search as sort of, well, from the start state, I'm just going to generate where my jump points would be. And in this case, we'd have a jump point here, we'd have a jump point here. So we'd come this way, we would come this way. We would have a jump point on this side of this obstacle. We'd have another one on this side of the obstacle. And depending on how these obstacles line up, we may then generate another jump point back here. And we wouldn't necessarily generate a jump point on this side of the obstacle because it's actually blocked in the shadow of that obstacle. So I might show here and say, well, look, you know, instead of generating 8 neighbors, I've only generated 1, 2, 3, 4, 5 neighbors here. And this looks like it's a very efficient search. But what's actually going on is that jump point search is computing the entire canonical ordering. So jump point search is running this way, scanning here, it's scanning here, it's going this way, it's scanning here, it's going down this way, and it's scanning all the way here. And it's going this way, scanning here, and scanning all the way down here. So in one step here, also here, so in one step of this expansion, although we are only generating 5 states to go on the open list, we're actually scanning the majority of this map in order to get these 5 states that are on the open list. So jump point search has an implicit overhead of the scanning process. Again, if this is not pre-computed, which can be done. And so in general, what we can ask is like, what is the worst case of jump point search as compared to A star? And what we would see, if I put the start up here, and I put the goal just a little bit behind an obstacle down here, what I discover is that if I run, sorry, that's the start. If I run A star, so we'll do A star in red. what A star is going to do is A star is essentially going to go directly towards the goal because it'll have a near perfect heuristic. And then it'll have to do just a little bit of extra work around here in order to find the way around the wall to get to the goal right here. Now let's look and see what happens when I run jump point search. What jump point search is going to do is as it comes down here, it's actually going to scan in all of these directions. And so jump point search in practice is actually going to look at the entire map. Okay. So in this case, A star is going to be looking at basically O of n nodes here, where jump point search, if n is the dimension of one of the maps, where jump point search would be looking at n squared. So depending on the cost of scanning the entire map here, which is very cheap compared to open list operations, but it is, when there's a difference here of like n squared versus n, if we scale the size of this map, have a relatively open map, then the running time of jump point search is going to get rather large compared to just running A star. And of course, there's caveats here. It depends on the type of map and other things like this. But there are these cases where jump point search can be very, very inefficient. If we can afford the pre-computation to say, actually, there's no jump points over here, so we don't have to worry about it, then jump point search will be fine. But in practice, we won't always be able to do that. And so this is a problem, and it suggests that we need maybe a different version of jump point search, which is going to be bounded jump point search. And what bounded jump point search says, look, I'm willing to jump, but I'm going to limit how far I'm willing to jump. So this is just jump point search. I'm going to generate what I generate the start. I'm going to generate the goal. I'm going to generate the jump points. And then I'm going to have some policy that's going to tell me how far I'm willing to jump. And so, for instance, I might say I'm willing to jump 4 steps. I might also say, well, I'm only willing to jump to, to locations if I'm on a grid map. I'm thinking about jump to locations that have an x and y coordinate that, or x or y coordinate that is modulo 4. This will just make sure that maybe my jump points line up. So there's a number of different policies we could use here for doing bounded jump point search. But the idea here is because it's bounded, we know that in a case like this, we'll never actually jump these long distances. We're always going to stay within some bound here. And this reduces the worst case of jump point search from n squared back down to O of n, as long as my bounded jumping is bounded by a constant. And the number of states that I could see there would be limited. And it's easy just to show this. So this isn't a hard algorithm if we have jump point search. It's easiest just to show how this runs in practice. So we're going to run on the same problem here, bounded jump point search. And what we see is in this case, we're jumping out, I think the distance is 4 or 5. So we're going to generate jump points. And we're also going to generate the states that are according to the policy that are no more than a fixed distance away. And if we look at sort of the total area of the states that we've seen here, there's states out on the right, upper right of the map, and on the bottom right of the map that our jumping policy normally would have scanned those states. But here we're limited in how far we're willing to jump. And where bounded jump point search works, like it's going to depend on my state space. If I go into 3-dimensional space, then it could be very costly to do this jumping procedure. So we might want to bound that particularly in higher dimensions of our space. And it's going to depend on your, the exact amount you want to jump is going to depend on, for instance, the efficiency of your open list, the efficiency of your ability to scan the grid. But there's going to be usually some trade-off where, and again, depending on the map, the more open the map is, then the more bounded I'm going to want my jumping to be to avoid this n squared overhead. Okay. So this gives us our first set of algorithms, and these are really saying, look, if we understand that our canonical ordering is really just a modified state space where we're using these extra constraints to limit the number of successors that we have, and then we have this other policy that says, look, well, in certain cases, instead of putting a state into the open list, I'm going to actually generate its successors recursively, and I'll have some policy that says when I put them into the open list. then that's going to give us canonical A star, which just says follow the canonical ordering. And then when we think about our policy, this gives us jump point search and bounded jump point search, that we have a policy that says what we put in the open list. Bounded jump point search says, well, listen, I'm going to go according to my policy some fixed distance. Jump point search says I'm only going to put jump points, the goal, and the start in the open list. And so this is really key. Jump point search is not actually a separate algorithm. In fact, jump point search is not a replacement for A star. Jump point search is A star on top of a world representation of the start state, goal state, and jump points. Okay, so this is really important. Jump point search is not a better algorithm than A star. Jump point search is A star. It's simply A star on a different representation of the problem. Going back earlier in the course, what we see is that when we think about algorithms, so a bidirectional search is something that can be fundamentally better than A star. It's a very fundamentally different search. Jump point search, though, is exactly A star. And we could think about bidirectional jump point search because it would just be search on this canonical ordering. Bidirectional jump point search, you have to be careful because you need to use the same ordering in the backwards and forward direction, or they have to be compatible with each other. But we won't get into that here. But again, I'll just say it one more time. So jump point search is A star. I'll just write it here to make this, highlight this. This is A star on the canonical ordering. The same as we set it up here. This is A star on the canonical ordering. This is A star on the canonical ordering plus jumping. Okay. So the idea here is we've actually reformulated our state space. By reformulating our state space, we can now use A star on this reformulated state space with a canonical ordering and jumping in our successor generation policy. By changing our policy for successor generation, now we run A star on it and we're fine. And bounded jump point search is just a different successor generation policy, but we're still running A star. There are some minor caveats we can think about that are slightly different here. And the only thing that's really different is that when I come to a state from multiple directions, typically I would think of this as being a duplicate state. So if I, just thinking abstractly here, I have a state, maybe I've come to the state from this direction, I've come to it from this direction. And the question is, well, what is a state? Is a state just an XY location, or is it an XY location plus our parent? It does need to be an XY location plus our parent, but it ends up, actually, I maybe should move this because this isn't actually a jump point here. So sorry, let's just be a little bit more precise. Let's move our obstacle over. Okay, so we could come at it here, and let's put another obstacle here. Okay, so maybe I can come to this state from multiple different directions here, and maybe all of these reach it with the exact same cost. So the question is, do I have to keep 3 copies of the state around, 1 from each of these different parents? This is totally not obvious, but for jump point search, the answer is no. It can be shown that if I reach the state with the same cost from different directions, then you can verify that that any other path to other states will be preserved, and I don't need to preserve and I can keep just one of these paths to here with one of these parents, and the canonical ordering will still preserve shortest paths to all other states. But okay, so that's the one complication, is how do we handle, is this state a state plus a parent, or is it just a regular state? In the most abstract view, we would have to think of this as a state plus a parent, because the parent is needed to generate the canonical ordering. But in jump point search, on a regular grid, we have the property that we don't need to think about the parent when doing this comparison, as long as I just keep one of these or update the parent when I find a shorter path. Okay, so that's the only thing that's different about jump point search than A star, is this issue of where is the parent sitting around. Bounded jump point search then, of course, is the same thing again. And now what we can do is we can start to think about, well, if this is really just A star, then why not just use weighted A star instead of A star? So we can now have a weighted jump point search, which is, it's just jump point search, But our best first search is going to be, I'm going to use f is equal to g plus w times h. And nothing has to change because this is just A star. Then when I want to run weighted jump point search, well, this is just weighted jump point search. And here, so when we introduced weighted jump point search, we didn't know about these phi functions, but we could also use phi functions that were described earlier in the class. So we could use like piecewise convex downward, pwxd, xdp, whatever. We can use these different use these different phi functions on top of here as well. We'll still get bounded suboptimal algorithms that will find bounded suboptimal solutions, but we just replace the A star portion of the search here with a weighted A star portion of the search, or some other phi function that we want to use to find suboptimal solutions. So this is important because now, and this is why I was making this point, is now that we understand jump point search as simply being a best first search, something like an A star search, just on a different type of map, then, or sorry, a different type of representation of our map, then we can understand that we could also apply other algorithms to it. So let's take a look and see what happens. We're going to switch to a different map here, just because we want to use by using a larger map, we're going to be able to see the difference in approach. So this is running a regular jump point search on this particular problem, and we're going to watch it searching out here. The goal is inside the room on the bottom of the map. So the goal has just been reached right there. It's in the middle of the room, or the right-hand side of the room. I apologize, you can't see the mouse on this recording. But anyway, if we look at the search here, the important thing to notice is that, well, so one thing we would notice is that actually maybe we should be using a bounded jump point search here. The search will actually have scanned all the way to the far right-hand end of this map. So this is an expensive map to scan. But we do notice that the search is going up into the top part of the map. And when I go ahead and use both on the left-hand side and on the right-hand side, and when I use a weighted jump point search, then we're going to see that the search now is a lot more greedy. It doesn't go into the top part of the map on the right-hand side, and on the left-hand side, it doesn't spend nearly as much time in the top of the map. It goes much more quickly. It gets towards the goal much more quickly, and then gets in towards to the actual goal state much more quickly. So this is a much more effective version of jump point search if I want bounded suboptimal solutions. And overall, we're still finding fairly high quality solutions here. These jumps, we get to jump quite a long distance here. So we're not, because of the jumping, we're actually not quite as prone to introduce some of the suboptimalities we might when I'm sort of one step at a time can be suboptimal. But I don't, to my knowledge, no one's ever actually implemented the phi functions and seen or tested them with jump point search on these sort of maps. So it's an interesting question, but I expect that with the phi functions here, we'll also see really good performance. Okay, so that gives us weighted jump point search, which is a fairly simple modification here. And the last thing we're going to go to is Dijkstra's algorithm. And basically what we're looking at here is, hey, so I've got this other representation of my domain, and so there's now with this new representation, I can put it in A star. I've got jump point search, which is sort of the maximal use of that. I've got bounded jump point search with sort of a limited use of that. I can put it in these other types of search algorithms. And now we can think about, well, what about Dijkstra's algorithm? So the difference here is all of the previous things we were looking at were sort of point to point. You give me any state, start, any goal, and I want to get the shortest path between them. But something that we're often doing in search is maybe we want to do a single source shortest path. We want this distance. Maybe I'm starting at the goal and going in reverse, but I want the distance from every other state, from one state to every other one. So for instance, when we're thinking about our differential heuristics, those require single source shortest path search. And if I'm doing them on a grid map, then maybe I can use the canonical ordering in order to do this more efficiently. And so I'm going to describe this a little bit of a high level, but let's look at canonical Dijkstra. And the idea here is that typically what happens, so when we're done, we want the shortest path to every state in the state space. And typically what would happen is in jump point search, if we think about what goes on the open list, well, you know, and what goes on the open and the closed list would be, I'm going to be jumping and I'm only going to be putting my jump points. So if I'm going here, I'd put a jump point here on the open list. I would go by here, I'd put this on the open list. I'd come down here, put this on the open list. And if there's space under this obstacle, you know, I might put this state on the open list as being a jump point. But all of the states that are inside here, we would just ignore them because I don't care about them. They're not the start, they're not the goal, and then they're not the jump points, which I need to continue my search and to avoid duplicates. But Canonical Dijkstra says, well, listen, I want the distance to every other state. So what I'm going to do is as I'm doing this search, what we're actually going to do is we're going to fill in all of these states that we scan. So we think about these scans that we're doing through the entire search here. We're going to fill all of these states in with the G cost that we find when we scan to those states. Okay, so we're doing the scanning, and now we're going to immediately into the closed list, actually. So this is closed list. We're going to mark down the distance that we found to these states. Okay, and now what happens is that, let's say I choose the next state to expand. Maybe it's this one right here. So we're going to do this one and then this one. And what we would do here is, well, I'm going to generate my canonical ordering. So my canonical ordering is searching up and out, and then I'm going to generate this as another jump point. And so what's going to happen is, and I'll just use a slightly different color here, is we're going to now come out, and as we scan all of these states, we're just going to write down their G costs because, hey, that's the G cost where I reach those states. And I'll do the same thing down here. I'll write out all their G costs. And now there's something interesting that happened. Okay, we've written out all their G costs, and actually on this side, I will get one jump point right here. But something interesting is going to happen. I'll draw this in red. And down here we had, and let me just zoom in on this to make it so you can see this really clearly. Down here, what's happening is we've got this path that sneaks inside here. And if we think about the path from here to here to here, this is likely to be shorter, or it is going to be shorter than the secondary path, which I'll do in purple, which went from here to here. So what that means is actually there's going to be some segment of states here, and I don't know exactly what it is, but we'll just draw sort of like that. There's going to be some segment of states which we actually found with suboptimal cost. We found with suboptimal cost because when we came to those states, we went around the top instead of the bottom, and when he generated this ordering, we just flew through and wrote down all their G costs. So what's going to happen here is when I come and do my next expansion on this state down here, what we're going to do is we're going to actually be putting these states, let me make this just a little bit skinnier. We're going to be actually putting all these states, we're scanning them, so we're going to put their costs in. And then we're actually going to continue here, and we're going to fill in inside this region where we find shorter paths. We'll fill in all the shorter paths costs that we found. And actually what's going to happen is we're going to find the shorter path to this state, and we'll update that cost. And so then actually, because we found a shorter path and it wasn't a jump point, we can actually remove this from the open list because it's no longer a state that we need to consider because we found the shorter path in this region down here. Okay, so what's going to happen now is we're immediately writing states to the closed list, which we did coming this direction. And now when we come back to this direction, we're going to find these states, which we now find shorter paths to, which sort of represent what the actual shortest paths are in our state space. So the same thing is going to happen over on this side of the state space. So we'll write this in red again. As we come here, we're going to start to generate these paths. And what we'll discover is that this path here is actually shorter than the path that was coming this direction. So what we're going to want to do is there'll be some region here where we now have shorter paths. And actually what could happen is this state could turn into a jump point for going back in this direction that is allowing us to fill in some of the shorter paths that we would have found over here. Okay, so canonical Dijkstra algorithm is like Dijkstra's algorithm. or it's sort of like jump point search. But as we do this scanning, we immediately write all the G-cost into the state space, with the caveat that some of those may be incorrect. And so I might have to I might have to take these states. I might have to decrease their G-costs later on when I find a shorter path to them. I might have states that were on the open list. I might find a shorter path and have to put them on the open list again because there's still a jump point. Or I may take them off the open list. In both of these cases, actually, they would stay on the open list just as a different jump point. And I might discover jump points that weren't previously discovered. So it's possible there could be a jump point, not in this map, but there could be a jump point sitting out here. Maybe I'll draw where we could get something like this. Like there could be a jump point sitting out here that was generated, not as a jump point, but actually when I come around the corner here is a jump point again. But generally speaking, I'm going to follow my canonical ordering. I'm going to write my G-costs. Whenever I find a shorter G-cost than I found already, I'll continue to update those. And then when I find a state that's a jump point, I will put that into the open list. And so we're going to, in Canonical Dijkstra, we'll actually see these large swaths. We'll actually see what jump point search is doing when it's scanning the map because we see it in the Dijkstra portion of the search. So the easiest way to understand this is actually just to watch this search run in practice. And oh, actually, it looks like my video is not running. So just a second here, I'm going to put this, make sure the video is running in here. So here's an example. We're going to use this example to look at what Canonical Dijkstra's algorithm does. And in this problem, we're going to run it really fast first, and then we'll run it much slower, and we'll step through what's going on. So we're going to start with the yellow state, which is towards the upper left portion of this map. And we're going to do Dijkstra's algorithm, but instead of just sort of doing one node at a time, step by step, we're going to be doing big giant regions. So let's watch this run, and wow, there it goes. It's really fast. Okay. So let's go and watch it again more slowly, and then I'll step through it step at a time. So we can watch here, we're doing big jumps at a time, and these are really the scans of jump point search, and those are getting us big portions of the state space. So let's go back and watch this. So we started the start state. We're going to follow our canonical ordering until we reach jump points, and that gives us all the states here. We're going to immediately write down all the G-costs of those states, and so that's labeling according to the color here. And so these states ends up that we have, at this point, we actually know that we've reached them optimally because we're following the canonical ordering directly there. But at any point after this, we're not guaranteed that we're doing that. We're going to come to the yellow state here. And so we're going to do that one next because it has lowest G cost. And so we expand out there. We don't get very far because of the jump point. And now continuing by G cost, we're going to go up and spend some time at the top. So the first yellow state at the top, the yellow state is always the next state to be expanded. It's going to get us up into that top area, again being blocked by jump points. So we've just filled in a whole bunch of distances there. And now we're going to come around the obstacle around the top side. And so as we come around the top side, we're going to follow the canonical ordering. And you can see there's this sort of red line that's drawn there. The red line is not necessarily the delineation between the shortest paths. Or it's related to it, though, just based on the way that I was running the algorithm for generating the canonical ordering that's being drawn underneath here. But we can watch that run, and basically we see that we just follow this, and we're going to generate all these states. And not all of these states will actually have been reached optimally, though, because we're going around the top instead of around the bottom, which is slightly shorter. But we've written in these distances, and now we're going to continue. So the next shortest state is now the one that was back close to the start state. And here we're going to follow the canonical ordering. And when we do that, we start to get these purple states, which are states that we've now found a shorter path in the close list. And so, as I said, those are the purple states. We have a jump point, which is so we had a jump point coming down from the top, but we're going to find a shorter path to it. And so that jump point that is in the upper left-hand corner of the purple states has now actually been converted from a jump point search going down to a jump point search going to the right. And then the other thing to notice is that there is a jump point search which is like a turquoise color at the bottom of the purple region. And that's a jump point search coming left to right. So we haven't finished exploring around the obstacle there. We'll see that in a minute. But we're going to go back up top, and we're going to finish some of that, filling in the states there. Now we're back to the canonical ordering, continuing in the middle. There's actually only one state. Remember, we're going left to right. So we fill in one state there. Now we'll go back to the top and fill that in. And now these purple states, we've all found shorter paths, and we expect then actually we're going to continue to fill in those shorter paths, which we do. But as we fill them in, we follow the canonical ordering, so it goes down and to the right. Because these, remember, we're coming from the left, so they're going to go down and to the right, and we'll actually be able to fill in all the way across to the bottom of the map there. So these are all being filled in with their GCOS, and then we'll continue to do so in the remaining regions of the map. So Canonical Dijkstra's algorithm here is using the same ideas that we've used to think about this. What's interesting is we're thinking about sort of this abstraction of the map with the constraints in it, but we're actually, because we're scanning through the low-level map, we're actually going to write all the costs in as we do that. And we have far fewer states on the open list. We're getting to write the G-cost of many, many states really quickly. So this is much, much faster than a regular Dijkstra search on this map. And so if you're wanting to do like single source shortest path on a grid map, the Dijkstra, a canonical Dijkstra algorithm is a much more efficient way to do that. And it still preserves the shortest paths. And so again, just to summarize what we've seen in this lecture is we've seen that we can take these algorithms that were designed for running sort of in regular state spaces, and we've basically introduced a new type of state space, which is a grid map with this canonical information about our paths. That canonical information, if we're careful about it, or because it depends on where we come as a parent, then we have to be a little bit careful in generating these new algorithms for the state space. And so here we can see that we are able to modify with a little bit of work. So it's not just necessarily a direct drop into the Dijkstra's algorithm version, but with some very slight modifications, we're able to end up with new algorithms that are more efficient on this underlying state space. So this really shows us the power of transforming our state space. And in the next lecture, we're going to look at how we can add constraints to other search algorithms, or in other ways, we're going to do pre-processing that's going to give us constraints. And so we'll look at 2 ways of doing that in the next 2 videos.